everyone, welcome to the next session on finite element analysis. In this session, we are going to discuss about the sources of error in FEA. Finite element analysis is a powerful numerical technique, but like any other method, it is subject to various sources of error. Understanding these sources of error is crucial for obtaining accurate and reliable results. We will discuss some common sources of error in FEA. First is due to mesh density, error due to coarse mesh. Using a mesh that is too coarse may lead to inaccurate results, especially in regions with rapidly changing stress or strain. Increasing mesh density can reduce this error. So if you must have gone through the ANSYS videos that I have created, you will see that there are three types of meshing possible. One is coarse, one is medium, and one is fine. Coarse means the element size is quite large. Medium means element size reduces, and fine means element size further reduces. So when you create finer meshes, what happens is you are actually focusing on that area where the stress or strain is more. So when you actually focus on that area, you are getting better results. You can compare this and create an analogy with the cameras which are available these days. If you look at the cameras available back in last 5 to 10 years, you would see that the picture quality was not that good. The reason is the number of pixels defining the picture were few. For example, you take a picture of a tree and there are say 100 pixels defining the entire tree. But if you compare it today, in today's cameras, you would find that there will be lakhs of pixels defining that same tree. So what happens is you basically can zoom in and you can figure out the various features available on that tree. Say a different shade of color of the leaf, or a pattern of the leaf, or a pattern of a branch. So such things also happen in this result, wherein you actually zoom in and you get better results. So that's all about increasing the mesh density, which is going to reduce the error. Next is the element type. Using an inappropriate element type for the problem at hand can introduce errors. Using elements that do not capture the physics of the problem accurately may lead to inaccurate results. Choosing a correct element type is very important. In some other session, I will take you through the element types in FEA also. You will get a better understanding of this concept. Next is boundary conditions. Incorrect boundary conditions is what can lead to sources of error. Applying incorrect or inconsistent boundary conditions can introduce significant errors. It is crucial to ensure that boundary conditions accurately represent the physical constraints of the system. The next reason for error is the material properties. Errors in defining material properties such as Young's modulus or Poisson's ratio can lead to inaccurate results. Obtaining accurate material data and inputting it correctly is essential. Suppose if you are discussing about plain carbon steel, see to it that you take up the correct values of the properties that are supposed to be fed into the software, and then you go for the analysis. So Young's modulus and Poisson's ratio, suppose if you go for structural analysis, are the two important parameters. So see to it that you give correct values for it. The next reason for error is convergence. Convergence in FEA refers to the stability of the solution with respect to mesh refinement. We will be discussing in detail about convergence in the upcoming session. Convergence basically means, suppose if you are discussing about a step bar and you want to calculate its deformation, you can calculate it by using the strength of material formula. That is called as exact method. Say by using strength of materials, you get the value as 2 mm. But that is the exact value required. But when you use FEA, you are not going to get 2 mm as a deformation. You will get little lesser than it. Say you can get 1.4, 1.5, something like that. The reason is the solution has not converged towards that correct value 2 mm. So if the solution is not converging towards the accurate value, then you get a little bit of error. For example, 2 mm is the required value, and suppose if you get 1.5 mm as a deformation, so 0.5 mm is the error. Insufficient convergence can result in inaccurate results. Convergence should be checked and confirmed by refining the mesh until the solution stabilizes. in FEA, what you can do is you can set the accuracy of convergence, and accordingly you can reach to the answer which is obtained by exact method. The next type is called as numerical integration. Numerical integration is used to evaluate integrals in the finite element formulation. Errors can arise if the integration method is not chosen appropriately. Higher order integration schemes may be necessary for accurate results. So you can go for better numerical integration techniques such that you get better results. There are various types of numerical integration techniques like the trapezoidal rule, or there's midpoint rule, Simpson's rule. So you can choose the method and then you can decide that by using a particular method what kind of error is obtained in the system. There are various formulas for calculating the errors also of the various rules. So accordingly you can decide. The next reason for the error is the element distortion. Elements with distorted shapes, say if they are highly skewed or nearly collapsed elements, can lead to inaccurate results. Checking and improving the quality of mesh is essential to avoid this source of error. The next one is geometric nonlinearity. When you neglect the geometric nonlinearity and you assume that it is linear and you just want to get the solution somehow, this can also lead to error in the solutions. So in problems involving larger deformations or displacements, neglecting geometric nonlinearity can result in errors. You can check the videos that I have created on nonlinear FEA. There you will figure out that when the deformation was going large, then I chose to go for nonlinear system and I have changed the system from linear to nonlinear and then taken out the results. Otherwise, what you get is an error. Sometimes the software also indicates that there is an error, and if it doesn't, then you can just go ahead with it, but yes, there will be errors in your solution. Linear assumptions may not be valid and geometric nonlinear effects should be considered. Time step size for dynamic analysis. Inappropriate time step size. In dynamic analysis, using an inappropriate time step size can lead to errors. Suppose if you are doing a dynamic analysis of transient thermal type and you need to choose the time step. Suppose if you give a very small time step, then it will capture your results properly. But suppose if you give a larger time step, then what happens is you're not able to capture the error in that time step. Suppose if you give from 0 to 0.1 to 0.2 to 0.3, then what happens is, suppose if the error is not captured in 0.1 to 0.2, then you will find that you're not getting the error. In that case, you may have to go for a time step of 0.01 or 0.001 based on where the error is situated in the system. So the time step should be small enough to capture the dynamic behavior accurately. Then comes the solver settings. The choice of solver settings and algorithm can impact the accuracy and convergence of the solution. Selecting appropriate solver settings, especially for nonlinear problems, is crucial. You can again go through the videos of the analysis. You will figure out what kind of solver settings are required and what kind of changes I have made in them. Model simplifications. Overly simplifying the model to reduce computational costs may introduce errors. It's essential to strike a balance between computational efficiency and accuracy. So this is very important. You cannot make your model extremely simple and then go for its analysis. You need to strike a balance between its accuracy and efficiency as well. Then comes contact and interface conditions. In simulations involving contact between components, errors can arise if contact conditions are not accurately represented. Inaccurate modeling of friction or separation can lead to unreliable results. So you need to give proper interface and contact conditions in FEA. Assumption of linearity. Assuming linear material behavior in situations where non-linearities are significant can result in errors. So we generally go for assuming that the material behavior is linear, which is not the correct way of solving. You need to assume non-linearity where it is required. Non-linear material models should be employed when appropriate. Uncertainty in input data. Variability or uncertainty in input parameters such as material properties or loading conditions can lead to errors. It's important to account for uncertainties and perform sensitivity analysis when possible. So overall, we can say that addressing and minimizing these sources of error requires careful consideration, validation, and verification throughout the entire FEA process, from problem formulation to post-processing, right from when you start making your geometry, assigning material properties, to getting the results. All the steps are where you need to check for the sources of error. Thorough model validation against analytical solutions or experimental data can help identify and reduce errors in FEA solution. So with this, I conclude the session. I hope you have understood the concept of sources of error in FEA. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.